We'll start with arrays. Previously, you could store one thing at a time per variable. Now, you can store a collection of different items into the same array. To declare an array, we use the same syntax as we did for variables to set the array name, but we use these square brackets in front of the data type to indicate that we're declaring an array instead. Now, we can directly assign values to the array like this using curly brackets, or alternatively, we can define an empty array of size n like this. This array that we call integers is a collection of 5 numbers. Note that trying to put any other data type into this integer array, like a string or a double, will cause an error. Now let's say you want to change the values in this array. You can access individual elements by writing the array name, followed by the index you want to access in square brackets. The first item always has an index of 0, so this will point to the first element in the array integers. And here will point to the second integer of the array. Then you can use the same syntax you would use to change a variable's value. So this code would change the first element in the array to 13, and this code would change the second element to 6. Now let's look at how to traverse through an array. One way is to use the dot length operation. With this, you can use indexes to individually access each element. So here we have an array of numbers with 7 numbers stored inside. And this for loop starts at I equals 0 and increments by 1 each time. And this code prints out numbers 0, numbers 1, numbers 2, and so on until 6, as the length of the array is 7. So here, if we run the program, we can see that it starts at 5, 3, 8, 1, 2, 9, 4. There's also a nice trick to simplify this with for loops, called the for each loop. This code over here means repeat the loop for every element present in the array, and every element that it loops through is stored in the variable number. Then you can sequentially access the array's contents by using the variable number. So again, we've got 5, 3, 8, 1, 2, 9, 4 printed as well. You can also nest arrays inside of arrays. This results in higher dimension arrays, or 2D arrays. To define these, you first need 2 sets of square brackets next to the data type, as opposed to 1 pair for regular arrays. Then, if defining the values directly, you need to nest the subarrays into a larger array, like this. So we have a subarray here, a subarray here, and a subarray here, which are all contained within these outer curly brackets. If you want to create an empty 2D array, you need to use 2 square brackets like this, specifying the number of rows and columns. So here, we're declaring a 2D array with 3 rows and 3 columns. You can think of a 2D array like a matrix of data, where the subbed arrays represent different rows, and the data takes up different columns. To access different parts of a 2D array, you can do one of 2 things. If you want a specific subarray, so a specific row, like this one, you can put the row index like this, and this will return the specified row. And this row is a 1D array technically. So you can store this, so we're storing this inside of the variable row1, and this row1 variable is the type integer array. And so this row1 stores this row, row2 stores this row, and row3 stores this row. If you want a specific element in a specific row, you can put the row index over here, then specify the column index. This will return the specific item in the specified row and column. To iterate through a 2D array, you need to use nested for loops. If you're using indexes, you can use this kind of syntax. It's basically what we looked at earlier, but you use the amount of rows and columns for your stopping conditions. So here we have I is less than 3 and j is less than 3 because this 2D array has 3 rows and 3 columns. Then you put the loop variables I and j like this. If we run the program, initially I is equal to 0 and j is equal to 0. So this prints out the element in row 0, column 0, which will be this number right here. Then j increments by 1, so it'll print out more numbers 0, 1, which will be this number. And then increments again, 0, 2, which will be this number. Then I increments by 1 and j resets to 0, so it'll print out this number, and so on. It's a bit more complicated with for each loops. So for your first loop over here, you need to retrieve each row in the array like this. And then for the second loop, you need to retrieve every element in the retrieved row. So notice how the data type here is int array, because each row is technically just a 1D array. And then we just do int call, so for every element inside of this array row. And so this variable, column, or call, will contain every element in the 2D array over the entire loop, going through each element in a row before moving on to the next row. So again, it'll move in the order 2, 9, 4, 1, 7, 5, and so on. So let's try just run the program. And there we go. We see 294.175.386. And then it starts again because, of course, we're doing it twice. 294, blah, 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 blah. So that's the basics of arrays in Java. But one key limiting factor in arrays are their fixed sizes. We can circumvent this problem using something called array lists. Array lists are not part of the fundamental Java language, which means we must import the array list package at the top of a program like this. Array lists are dynamic in size, and we can add as many elements as we want to the array list, although they must all be of the same data type. To define an array list, we can use this line of code right here. The array list R can store as many integers as the user wants. The same index rules from arrays apply here too, where the first element starts at 0 and it increments by 1 every time. To add elements to array lists, we use the .add function. It assigns the next available index to the element in the brackets. So here, 3, 6, 7, 2, 9. To remove elements, we can use .remove. But this time, in the brackets, you must specify a valid index to remove. We can also get the element at a specific index using .get, or get the index of a specific element with .index of. .size gives you the size of the array list, and .set allows you to replace the element at an index with another value. Then, we can use a similar method to regular arrays to print out each value in the array list. So here, we use a for each loop. Let's now look at two special data structures, stacks and queues. You can think of a stack data structure as a literal stack of plates. When you add a new plate, the plate is put at the top of the stack, and as you add more plates, it stacks up. When you want to retrieve a plate, you have to take it from the top of the stack. This is the principle of a stack data structure. It operates using the last in first out principle, or LIFO. There's 4 key operations that you can do on a stack. First is push, which adds a new element onto the stack. We've added 5 numbers to the stack here, which results in the stack looking like this. There's also pop, which retrieves and removes the element at the top of the stack. So since pop1 stores the first pop, it stores 8, and pop2 stores 3. And the stack is then left looking like this. There's also peek, which only retrieves the element at the top of the stack without removing it. So the variable peek here stores the value 9, but 9 isn't removed from the stack. It stays. And lastly, is empty, which checks if the stack is empty. Since we still have elements in the stack, this print statement will print false, as you can see right here. Next up is a queue. You could think of a queue data structure as a literal queue of people. People enter the queue at the back of the queue, and people are removed from the queue from the front. This is the first in first out principle, or FIFO. Key operations include enqueue, which adds an element to the back of the queue, dequeue, which retrieves and removes the element at the front of the queue, front, which just retrieves the element at the front, and isEmpty, which checks if the queue is empty. Notice how these operations are all similar in function to stacks, but using FIFO instead of LIFO, and using different words to describe the actions.